You're listening to Gradient Dissent, a show about making machine learning work in the real world, and I'm your host, Lucas Bewald. Chelsea is an assistant professor in the computer science department at Stanford, where she works on robotics and machine learning. I'm always excited to talk to anyone about robotics, but her research is specifically interesting to me because she talks about how robots collect data and how they learn through play. I learned a lot from this interview, and I hope you enjoy it. Well, cool. This should be fun. I'm really excited to talk to you. And I guess the place I wanted to start is like robotics at a high level. Like looking through your work, there's all these like amazingly evocative videos of robots doing impressive things, and yet I have this impression that actually like making robots do like really meaningful stuff like in the real world is pretty hard. Like I have a Roomba in my house, but I don't use it that much and actually not much else. And so I was wondering if you could try to describe the state of the art of robotics and like what's possible and not possible today.
Yeah, that's a great question. So robots can do a lot of different things today in some ways. And in some ways, they also are, I think, quite far from the real world. So what I mean by that is many people have probably seen videos of Boston Dynamics robots doing really incredible things like doing a backflip, for example, or picking up an object, a crate, and throwing it somewhere. And we've also been able to have our robots do things that are pretty cool as well, often on robot arms. So like using a spatula to lift an object or being able to tear off a piece of tape and put it on a box. Fairly delicate tasks. So from the standpoint of these videos, it looks like robots are ready to go out into the world. They're very capable, but the catch is that they work well in fairly narrow scenarios. So the Boston Dynamics robots are tuned to be for a particular configuration, for a particular environment, and our robots are trained usually in a fairly narrow set of environments. And what this means is that if you change something about the environment, or if you change something about the objects that it's interacting with, then the robot behavior that you saw really starts to fall apart. And this is really unintuitive for people because we're used to seeing a person, if we see them do something impressive, we assume that they must be able to do other impressive things. And surely if you give them a different water bottle, they should still be able to pour water out of that water bottle. But the way that the kind of strengths and weaknesses of robots is actually quite different from people. And so in our research, a lot of what we're doing is not just trying to advance the dexterity of robots, but also advance what's often called generalization of robots, the ability for a robot to do something not just in one scenario, but to do it in any scenario.
And I mean, it's funny what you're saying about, robotics, because I think, 20 years ago when I was working on NLP, I feel like I would have given a pretty similar description of how these tasks like look impressive, but they're, very hard to generalize. But I feel like now it does seem like a lot of these NLP tasks, generalize pretty well. And there's been like such amazing breakthroughs in vision as well, where it seems like a lot of these vision tasks have really been, solved or like you get like, superhuman performance. Do you feel like there's a similar thing coming in robotics, or do you think there's something kind of fundamentally harder about robotics applications?
Yeah, so I think that something is coming, and we're already starting to make a lot of progress, but there's also things that are fundamentally different. So one really big thing that's fundamentally different is that we don't have data lying around on the internet of like how to control motors of a robot to tie its shoelaces or something. And whereas in natural language processing and NLP, we have Wikipedia. In vision, we have Flickr and all this image data on the internet. Now, that said, a lot of the data on the internet of images and text and so forth should be quite useful for robots to help them figure out how to see and so forth. And so it's not like we're starting completely from nothing, but it is different. And so a lot of the challenge is a data challenge. Now we're starting to actually get larger data sets and starting to aggregate data sets, starting to collect data sets to the point where we can actually train some policies, train some behaviors that generalize a little, like far beyond what we were able to do before. And I could dive into some specific examples if you want. But
please, yeah, no, I saw some of your work is really interesting on this. If you could kind of talk about some of the stuff you've done and other people to collect these large data sets, I think it would be surprising to a lot of people listening to this.
Yeah, so some of it has just been like, we want to put a robot, we just put the robot like somewhere and we like tell it to move its arm in a fairly random way that will like push objects around in a bin, and that we could just run the robots overnight and collect a ton of data. We did that for a while, realized that led to data that is kind of hard to use and fairly like, if the robot's just executing random actions, then it's only really going to push objects. It's never going to do something like pour water out of a water bottle. And so while we could collect a lot of that data, it wasn't like really nice data. Like the kind of like Wikipedia, for example, is really nice data because people are writing high quality content about stuff that has like a lot of knowledge about certain topics and so forth. And so we started collecting data that looks a lot more like a human actually operating the robot. So a human uses like a VR controller or actually guides the robot arm or something like that to actually show a demonstration of this is how you pour water from a water bottle, and this is how you pick up an object and move it over there and so forth. So we started to collect larger data sets that are collected basically by humans by controlling the robots. And with this, through work that I've done at Google, we've collected data on the order of 100,000 to 200,000 demonstration trajectories. These trajectories have correspond to a video as well as a sequence of motor commands to control the robot. That said, 100,000 is not that large by machine learning standpoints, and so we're still we're starting to do cool things with that, and we've been able to train policies that can do a lot more with that data than when you only have like 100 demonstrations. But it's still challenging, and so some of the work that we've been doing to build on that is one, actually trying to leverage pre-trained vision language models and then fine-tune the vision language model on that data. And if you do that, you can actually show that the robot will get semantic generalization. So what I mean by that is the robot in its own data, it's never seen a lot of different things. So for example, it's never seen, doesn't know anything about various celebrities, for example, and we asked the robot to pass a Coke can to a picture of Taylor Swift. And of course, it had never seen Taylor Swift in any of the robot's data. But by using a pre-trained vision language model, it's actually able to do that task and pass it to the correct person rather than other people. So it's able to kind of transfer this knowledge that's on the internet to robot control, which is pretty cool. And then we've also been trying to aggregate data sets across labs and also across robot platforms. And with that, we've been able to actually train a single policy that can control not just one robot, but actually 6 different types of robots, which I think is pretty cool as well.
And I mean, I guess like one thing that, kind of comes to mind for me is the pose estimation of humans. It seems like, I've watched a lot of work get done on that, and it seems very impressive. Like, could you think of a human body as sort of like a robot platform that you could learn from? I mean, certainly there's a lot of videos of people doing different things on their own.
Absolutely. So as I just mentioned, like we can actually train policies to control multiple robots. A human in some ways is just another body. And so we could train on that data as well. One thing that gets a little bit tricky is that for human data, we have the videos. We have videos of people doing things, but we don't know how you actuate your muscles to do something. And the way that we typically train these things, actually having that information is very important for the robot to understand how it should actuate its motors to cause some change. And so you do need to kind of extract out that. Some of it just comes down to pose estimation, and there's a lot that you can do with that. For more complex tasks, you might also need to figure out like more than just that, like forces or something. Yeah, if you can do good pose estimation, then that is like you can integrate that data in as well.
And I mean, I guess another, really kind of evocative area of research that, I saw you were kind of working into the robots learning live. And especially I thought like learning through play is so interesting. I mean, I don't know if you have kids, but I have 2 young kids, and like watching them learn to navigate their environment really feels like reinforcement learning happening. I mean, I'm curious, like, kind of if you think that's too much anthropomorphizing, AI or something, or kind of what you learned through that.
So one of my first projects actually at Berkeley, when I was a PhD student, there's a postdoc in the lab who was working on reinforcement learning for robotics, and the robot was learning through trial and error. And actually one of the tasks it was doing was to stack one very large Duplo block onto another Duplo block. And it looked a lot like a kid. It looks a lot like, I don't know, like play, like actually, I don't know, trying to figure out how these two pieces might fit together and then eventually getting better. And it was really cool. And it would actually, that system actually would learn how to do the task in like 10 minutes, 15 minutes, sometimes even less than that. And so you could see like the learning and the play happening before your own eyes. And that was really magical to me. And I saw that when I came to Berkeley, and I was like, I want to work on that. And so my first project was on reinforcement learning for robots. And it was actually to extend that previous system to learn a policy straight from pixels. So the previous system was fully blind. It was basically had its eyes closed and was trying to fit the blocks together. And we were trying to see if we can also have it learn how to see at the same time, and have it do things where, like, if the block is in a different position, can you actually perceive that and then put the block on there? And that project, we were actually trying to learn a neural network end to end that maps from images to torques on the robot's joints. And that was one of the first examples of end-to-end learning for robot control straight from pixels to torques. This was we were working on it back in like 2014, 2015. And it was, it worked. We were able to kind of concurrently learn both how to see and how to act. Anyway, this is a little bit of a backstory. And now I think that, reinforcement learning remains a really compelling way for robots to learn. I think it's really cool just to see the learning process happen autonomously. And it seems like the ability to learn from one's own experience is a really core aspect of intelligence. I think that if you only learn through mimicry, through imitation learning, which is what a lot of other work does, then I don't know, it seems like that's a lower level intelligence in some ways than a system that's able to learn from its own experience. And also, I think that the ability to learn from trial and error, I think, will be really critical to scale data collection, such that robots can actually collect their own data and learn from that, rather than having to have a human show them everything. You might still need a babysitter during the kind of trial and error process, but I think it'll be really critical for getting robotics to really work in the long run. Both in terms of scale of data collection during the learning process, as well as also during deployment. If a robot is out in the real world, if it makes a mistake, then you probably want to actually have it correct and learn from that mistake quickly, and be able to try something different such that it's ultimately more robust.
I see. So I'm far from an expert in your field. So I'm kind of curious how you even set up some of these tasks without using reinforcement learning. Like you have some very evocative videos on your website of like a robot dog learning to like pull a box, and then pull a box like while it's really wearing roller skates or something like that. And presumably it hasn't like seen that situation where it has roller skates on before the roller skates are actually put on the dog, because without your work, it kind of does what you'd expect and kind of slides all over the place. So what's going on there? Like, how are you framing that as a problem? How are you knowing if your technique is working?
Yeah, so we are framing that from the standpoint of it has some kind of previous things that it's learned about. It's learned how to walk. It's learned how to. It's also learned how to walk when like the back right leg is crippled. It's learned how to walk when the front left leg is crippled and so forth. But it's never seen anything like roller skates, or it's never seen a payload being attached to it. And then the goal was, can we, like, on the fly, as it's kind of trying to get somewhere at test time, can we have it figure out how to handle those new situations? And the way that we do that is is twofold. So a lot of approaches try to adapt just by fine tuning, and we do a form of fine tuning with a reinforcement learning objective, but that will lead only to kind of small changes to the behavior and slow changes to the behavior. The other thing that we do is we actually adapt at a higher level in the space of behaviors, such that actually at each time point it's kind of picking a different skill to deploy, such that if, for example, it's in a position where it needs to kind of slide forward on its kind of front left leg, then maybe you'll deploy a skill that will do that, and likewise for another skill. And by essentially dynamically picking which skill to use at test time, then you can actually adapt to these new situations.
I guess before I go too deep, and this is like an embarrassing question to ask, can you like walk me through when a dog is moving, like what the inputs and outputs are of the model or maybe the multiple models that you have, and what fine tuning would even mean in that context?
Yeah, that's a great question. So the inputs would be, so we have a number of sensors on the robot, and it's always going to be things from those sensors. Sometimes you may also have external sensors as well, but we've been doing everything with onboard sensors. And this will be like, you'll usually have an encoder on a motor that will tell you the angle of the joint. We'll also have like an IMU that will record the like acceleration. Another thing that we've done is to measure the velocity. You can measure velocity in a variety of ways. And so we'll usually feed that in. And then in some of our works, we'll also use a depth camera or an RGB camera, and that will be an input as well. And then the output will also be at the joint level. And there's a few different ways that you can control the joints, position control, velocity control, torque control, or something like that. Yeah.
Uh-huh. And then what is like what is the goal of the model? Like when you train the model, like what is maybe the loss function of this model?
Yeah, so when we train it, typically in terms of like doing research, we'll primarily focus on just having these robots be able to walk forward or run forward. And so the reward function is forward velocity, usually. You can also do things that are more complicated. We have a separate paper where we're training the robot to do like parkour-like skills, and you
cool.
And I guess the goal may also just be to run forward, but you put various obstacles such that it has to jump over something, jump over a gap, or be able to climb on top of a box or something, or dip under some sort of obstacle.
And I guess like in a context like that, or even like while walking, right? Presumably like you're not always actually like moving forward. Like how does it learn to, do things that pay off like later down the road?
Yeah, so that's why we need tools like reinforcement learning. So you can't directly optimize for forward velocity. You don't know, like you don't get gradients from the parameters of your policy that's outputting joint commands to like forward Cartesian velocity. And so tools like reinforcement learning allow you to so we'll use we'll learn a value function which estimates the sum of returns into the future, usually discounted, and then go from there.
I see. So you are framing these as reinforcement learning problems typically with like this dog robot.
Yeah, so typically we'll use reinforcement learning as a tool to optimize in one way or another. Now, when I was mentioning the adaptation for fine-tuning, we will be fine-tuning with reinforcement learning. For the behavior selection, we actually, for kind of adapting at a high level for different behaviors, in some ways we're using tools from reinforcement learning. We're actually using the value functions of those different skills as a signal for which skill is most relevant to a particular scenario. And we also additionally actually put a regularizer on top of it that makes this sort of selection actually work really well. But yeah, we're definitely using tools from reinforcement learning. There's also a lot of works that try to, there's a lot of scenarios where you may not know the reward function. So one of the things that's really nice about legged robots is that actually just like forward velocity is it's like a pretty solid reward function for learning interesting behaviors. But in other scenarios, if your goal is to pour water from a water bottle, you can't directly measure the reward. You don't there's no sensor that tells you how full is the glass. I guess you could have a scale and have a bowl on that scale or something, but even then you can't directly measure did water spill or something like that. And so there's a lot of works that try to learn reward functions or try to learn behaviors that incentivize or learn reward functions in a way that incentivizes diverse behaviors or exploratory behavior.
That's cool. And if you say you're trying to get a robot to just move forward, are you able to run that overnight in a lab? Or I just my experience with robots, my very limited experience with robots is if you kind of leave them alone for a while, something bad happens. Are you able to really run for hours or days on end successfully and test it?
Yeah, so our work with the legged robots is pretty recent. We bought the legged robot less than a year ago, so we haven't tried to do that yet. Although my impression is that labs that have done longer running experiments typically still require a person to help out the robot if it gets stuck. With the robot arms that we've used, we've been able to do experiments overnight where the robot is kind of collecting data and learning and getting better on its own without a person there. The robot can still get stuck. For example, it might one classic thing is it'll drop all the objects onto the floor and then it doesn't have any objects to play with basically. And it can't reach the objects. And so then it won't be collecting very useful data, even if the software stack is robust enough to have the robot run extensively. But yeah, generally we can, for the arms, we've been able to run them overnight for a day and a half. Usually all the objects will be on the ground before the robot before anything with the software stack breaks.
I guess with arms, my impression is that there are whole companies and huge research projects built around just picking up objects reliably. Is that true? And if so, why is that task so hard? I mean, that just seems such a simpler task than some of the AI breakthroughs that we've seen.
Yeah, grasping and picking objects is done. It's a big problem, and there are companies that are very focused on that problem, especially because it's very useful in warehouses and logistics and so forth.
Totally.
It's challenging because there's a very long tail of objects. In some ways, just like driving, there's just so many different scenarios and objects that you might encounter, rare objects that you would never think about. And so, yeah, that's part of it. The other thing, the other reason why it's not so that's, I think, one big reason why it's not fully solved. And this, there's just a very diverse set of strategies that you need to take to pick up an object. And it depends on if the object is is in a bin versus if it's on a shelf versus if it's in the fridge or something. It can actually get quite complex quite quickly. If there's another object on top of it, then you need to move that object out of the way. The other thing is that actually a lot of the robotics community wasn't using machine learning. When I started my PhD and when I was working on end-to-end learning for end-to-end deep learning for robotics, even any sort of machine learning was for robotic control was really not the norm. There was this huge conference on robotics and automation, and it had over 100 sessions, and there were only 2 sessions on learning and adaptive systems, and half of the papers in those 2 sessions were from my lab at Berkeley. So now, of course, that's changed a lot, and it's starting to become a lot more of the norm. But there was a lot of skepticism around machine learning. You can't prove that it's going to work, and the control approaches you can make some nice guarantees about if you make the right assumptions. But I think that to handle really long-tailed scenarios, to handle the diversity of objects you might want to grasp, you need tools like machine learning to help you out.
What do you think, like with machine learning, the state of the art is today? Like, can you make an arm that can reliably pick up arbitrary objects that you might encounter?
So my impression is that, or at least the startups that I've interacted with, they're acting like bin picking is solved. And that's not, and I think they're acting like that for a fairly large number of objects. I don't know if it's an infinite set of objects. Like in a lot of warehouses, like you're not going to have like a giant pumpkin like show up in your bin probably. And so there's going to be a distribution of objects that you'll see in bins that are kind of designed for those kinds of bins. And so it seems like, at least for like top-down grasping, that it seems to be solvable from what I've seen. And then it can get a lot harder. And so I think that for other versions of grasping, like from arbitrary surfaces, for like, I don't know, for arbitrary objects and so forth, I think it's harder.
Well, I guess, Chelsea, so another thing, that I hear from a lot of, other roboticists that come on this podcast and companies that we talk to is emphasis on simulation. Do you think that simulation is important for making robots work? And how does it sort of compare to the real life data collection that you're doing?
Yeah, so it's a great question, and I suspect I'll have a different perspective than other people you've talked to. So
awesome.
I think that simulation, it's gone quite far, and we use it for prototyping a lot, and also for legged robots, it's been quite effective for like you can actually train a policy for a legged robot and directly transfer it to the real robot, which is pretty cool. And actually the parkour learning that I mentioned, we did that fully in simulation and then just applied the robot zero shot in the real world, which is pretty nice, pretty awesome.
Yeah.
Now that sort of transfer is still quite finicky, and like you have to really tune things to get it right. And then for manipulation, for like robot arms, there's some things that you can definitely simulate, but I think that in the long run, if your goal is to build a robot that can do anything, I think the simulation will be a big blocker. There's a lot of things that I don't think we can easily simulate. It's also, I don't know, it takes energy and expertise to set up a task in simulation. And in the long run, it may be easier to collect data in real than to try to like set up the environment in the simulator and get the physics right and get the visuals right and so forth. So I think in the long run, especially for manipulation, I think that it's not necessarily going to be on the critical path. Also, if you look at if you look at computer vision researchers, language researchers, they're all using real data. And I think all the biggest results have been with real data sets. So yeah, that's what I think in the long run. As an example of things that like are hard to simulate, anything like when we eat, like skewering a grape with a fork, for example, really, really hard to simulate. And even if you can simulate it, it's not going to be faster than real time. Because you need to simulate at a very high time frequency. So, yeah.
I see. And I guess other people have talked about how things like things that are floppy, like folding clothes and stuff is hard to simulate. Is that right?
Yeah. So what's usually called deformable objects is hard to simulate. Another example is we actually recently started doing some real cooking tasks. And
cool.
If you want to simulate the process of food cooking, that's pretty hard.
Although it's like, I mean, that's a good example where I imagine simulating the process of food cooking is hard, but like cleaning failed food cooking also sounds very time consuming.
That's true. Yeah. So we're starting with imitation learning for our cooking tasks. So we don't have to have the robot very messily attempt to do things. In the long run, I hope that I hope that robots will be as efficient at learning new things as people are, such that I don't know, if a kid is learning how to cook things, they aren't going to make, well, they'll probably make a mess in the kitchen, but I mean, it won't be as bad as if a robot was trying to learn from scratch.
the kids won't be as bad, or if the
The
robot
kids
is
won't be
running.
as bad. Yeah.
I think you might not have kids, Chelsea.
No, I don't.
Yeah. Okay. Could get pretty bad. I promise. I guess. Do you have like opinion on? I mean, I just like household robots seem so like evocative and fun, and like is there? Do you have do you imagine like robotics applications coming to our house? Like I feel like just grasping could be really valuable. Like just like folding clothes could be like really awesome. Like I guess what do you? How close are we to that?
Yeah. So I think that for things like that, I am somewhat of a pessimist. I think that like I don't think it'll happen in the next 5 years, certainly. But I am actually really excited about progress in robotics right now. It does seem like we're at the point where if we throw good data to our robot systems, they do really well, and we're able to learn pretty complex tasks, even with a fairly small number of demonstrations, and then yeah, we can also get generalization, and yeah, the data that we throw at our models, it can actually learn it. So I'm pretty excited about where we're at. I think that a lot of it's going to come down to data, and getting data, getting data to cover all of those households, or to cover all the scenarios that you want it to handle is challenging and expensive. And so I think it's going to take a big upfront investment. I think there's just a huge initial cost into that data. And then once we have a robot system that's marginally useful, then it can collect more data, and hopefully that'll be kind of a launching off point. But yeah, I think that I think that's part of the challenge. I also think that there aren't, like, compared to like NLP and developing language models, there aren't that many people who work on robotics. And so the progress that we make, while I'm actually pretty excited about the progress, it's not at the same level as the progress that we see in other areas of AI.
Although that could change as, people get enthusiastic about the results, right?
Yeah, definitely. It also, I think we would need to be hopefully a little bit more accessible. One of the reasons why I think a lot of people get involved in like language model development is they just need a computer and I don't know, maybe some GPUs. And I guess maybe that does suggest that if, I don't know, if they need some GPUs, like getting a robot isn't, these days there's actually robots that are actually quite cheap relative to the price of GPUs. And we've been able to do tasks, quite dexterous tasks with robot arms that cost $5,000, which it's not like dirt cheap, but it's definitely getting down there. And it used to be that like the robot that I used in grad school was $400,000. So that's 100 times less about.
That feels like Moore's Law-esque. I mean, that seems like a good sign.
Yeah, absolutely. And I think that with like cell phones, for example, cell phones got a lot cheaper once they were useful for people, and once they were useful for people, there was the demand, and once there's the demand, then the manufacturing processes really make it a lot cheaper.
We've had people that have talked about robots kind of working best in like a human-esque or humanoid kind of form. Do you have opinions on that? Like, it does seem like a human form robot would sort of kind of fit into our world well. I think it's an evocative idea. What's your opinion?
And on one front, I think humanoids are overrated. I think you can really get quite far without the legs, just with a wheeled base and two arms. At the same time, I recently ordered a humanoid for my lab, so I can't say
Cool.
that they're too overrated. I'm really excited to start playing with it once it arrives.
Awesome. What about dog form?
Yeah, so we have a quadruped, and it's been fun to work with. I guess like there is something to be said in terms of like robots being human sized, to be able to do human tasks. And so going back to that question, we've started using a robot that has much smaller fingers about a year ago, and it's actually really cool that you can do way more interesting stuff compared to a robot that had bigger fingers, just purely because of the finger size. Now, going back to the dogs, I don't know if you want a companion, then maybe the dog form is good. I don't know, cuteness, I feel like also, I mean, certainly if you want to actually seriously put robots out there, I think that the form factor of the robot matters because people anthropomorphize everything. And so if it looks like a cute robot, it's something that then it'll be something that people want around and something they want to interact with.
Or maybe there's an uncanny valley, right? If it
Oh, certainly there's definitely an uncanny valley. And I guess what I wasn't saying it has to be realistic. I was saying it should be cute. And so
I see.
It doesn't need to be like a cute person if it's like if it just has the attributes of things that are cute, then and I guess as an example of this, we're working on putting a gripper on our quadruped so that it can pick up walk around and pick up objects. And currently our gripper is sideways, which kind of looks like a pincher robot or like a scorpion or something, which it looks kind of creepy and scary. And I think that if they rotated it the other way, it would look like a duck, or I don't know, it would look cuter, I think.
I see.
Unfortunately, I think we need to keep it this way because it's just for practical reasons, it's a lot easier to pick up objects. But even small changes like that, the robot is not anthropomorphic, or it doesn't look like a real animal or person in any way. But you can still, small changes can affect how it looks.
Well, I did feel like your dog on roller skates was pretty cute, and it made me wonder how well an actual dog would fare if it was wearing roller skates.
Well,
I think it might struggle more than your robot.
Online. Yeah,
Really?
You can look up videos online. It's actually, if you put socks on robots, they often actually they have this reflex that it's really funny. You can look it up.
All right. Well, maybe we can include some of those videos in this. Do you feel like you are at? People talk about superhuman performance, but do you feel like you're at super dog performance with your robot dog?
No.
Okay.
Definitely not.
I mean, all right, well,
maybe there are some dogs that are not very good. I'm not an expert on dogs, but yeah, no.
Well, I want to find a video of a dog with roller skates, and we'll see for ourselves. I don't know if we should run that experiment, but maybe someone else has. I wanted to switch to talking about your work on providing student feedback. And I was curious, so maybe you could describe the work, but I was also wondering how that related to your robotics work, or how you ended up, working on that as well.
Yeah. So we have a couple different works, and I guess I'll talk about the most recent one. And the motivation is that in computer science classes, a lot of classes will, as an assignment, have a student program a game or some interactive application. And so, for example, in Stanford's enthusiast class, they have students program Breakout. And on code.org, there is a game called Bounce that students program. And these assignments are actually really engaging for students because they actually get to build something and then interact with it, which is really cool.
Totally.
But also at the same time, it's pretty time consuming for an instructor to give feedback on or to grade, because they have to actually interact with the system. The way that TAs at Stanford grade the Breakout assignment is they actually play the student's Breakout game and try to find bugs. And there are some bugs that are actually really hard to find. One very classic bug is if the ball ends up getting hit by the paddle by the side, then the ball actually doesn't bounce off of the side. And this actually is, I don't know, somewhat common in the student assignments. And it's really hard to do this kind of skewering of the ball. And so we were trying to build a tool that can essentially automatically play the student games and then grade them, essentially, basically find the bugs in the students' games such that you can give that feedback to students. And if you can do this, then there's multiple things it could be useful for. You could use it to give immediate feedback to the students to say, hey, here's an issue in your program. Here's a bug and something that you should try to fix. And maybe here's a hint for how you can fix that bug. Or you could use it to help TAs grade faster and more accurately. And so we actually did that, and we developed a system. It works. If you give it data, you can train it on, and really, in principle, any game. And we trained it on both the code.org game and the intro CS game. And then we actually deployed it at Stanford, and we basically used it as part of the grading interface for Stanford TAs, where it would pre-fill the rubric, and then the Stanford TA would check the rubric that was filled in by our system. And then And then with our system, we found that the TAs were a little bit more accurate and a lot faster.
How did you train it? I'm trying to imagine, like, what is the what's the loss function there, I guess, or what's even the input and the output?
So we're using what's called meta reinforcement learning, and so it's a variant on reinforcement learning where you essentially in reinforcement learning you have one Markov decision process. You're trying to optimize one reward function in one environment. In meta RL, it's not just one environment and one reward function. You have many environments and reward functions. And this maps onto the student scenario because every student is programming a game. And basically every game from each student is a different MDP or a different environment. And then the goal is when you're presented with a new environment to be able to learn a policy that can play the game and seek out the bugs. And so we can set this up. We actually used a meta reinforcement learning algorithm that we had developed previously and actually mostly just applied it out of the box where the policy gets rewarded if it exposes information about the grade or if it exposes information about the bug that's present in the student's program.
I see.
And you can train policies that will try to expose that information. So if the bug that you're looking for is like what happens when the ball hits the ground, like does it properly like lose a life or whatever, and then for that bug we'll learn a policy that actually purposefully like avoids the ball hitting the ball such that the ball hits the ground and to actually expose that bug. So yeah, it's a form of reinforcement learning, and this kind of algorithm is also useful for things like robotics because robots might find themselves in lots of different environments, and if they can adapt to a new environment very quickly, then that's really useful.
Boy, I mean, it sounds incredibly like practical. Like, I wonder if you could look at, like open source projects and bugs that were discovered later or security vulnerabilities and, like how did you, I'm sure you thought about how to, is it possible to take in that direction?
Yeah. So we're working on, to start, we're just working on open sourcing the auto grader for Breakout, such that like other teachers at other universities could offer Breakout for that assignment. And then we're also trying to train it on other games such that if an instructor has another game that they're teaching, then they can get feedback on that.
I think there's a component to this where you gave the students useful feedback like a teacher might do. So how did you incorporate that?
Yeah, so what we do is our system plays the game, finds the bugs, and it could just directly give the grades to the students. Because grades have like real impact on people, we wanted to have an additional check and have a human in the loop. And so what we did is we had an interface where we showed the video and also the predicted rubric scores for each of the different bugs to a TA. And then the TA checked the rubrics, the pre-filled grades, and also watched the video, and then potentially made some changes to the grades and then submitted it. And so, overall, this made the graders a lot faster and a little bit more accurate.
I see. But there wasn't a component where the actual your algorithm is giving students feedback.
So we only deployed it for this for helping with grading, and the students get the grades and they get the feedback. But we're thinking about just directly giving it to students, and we might actually do that in a upcoming online course. Actually, just have it be a tool where students can like submit their program and get the instantaneous feedback. We decided to use it for grades to start, in part because we actually didn't have that much data in Python for this assignment because the previous time this assignment was offered, it was in Java. And so we didn't have a way to like really thoroughly test our algorithm on student data before deploying it, which is always a little bit scary. And so we knew that if there was a TA in the loop though, then we would be it would be more reliable. But now that we've actually more thoroughly tested it, we're pretty confident that we could use it to directly give feedback to students.
So do you plan to like roll this out to more classes and projects, or is that sort of outside the scope of your work?
Yeah, so we are working on open sourcing the auto grader for the breakout assignment. We actually submitted this work and it was accepted to this conference on computer science education. And as part of that, we're actually we haven't put out the paper that specifically was looking at this, deploying it at Stanford, but we're working on putting that out. And then we're working on open sourcing it, and we're also planning to host it on the internet, such that anyone that wants to like use it, they could just use it and submit their program and get feedback back, or teachers could use it to kind of get their initial grades. And then we're also thinking like you can train this for other games, and so we're planning on trying it for other games, not just for Breakout, such that we can have kind of a suite of auto graders and a suite of assignments for different teachers. And then of course these algorithms might also be useful for finding bugs in other kinds of software, not just in student programs, not just in education contexts. We've started to talk about that a little bit. It's still something that is kind of in the brainstorming stages.
I guess this isn't directly affected. I mean, this isn't directly your work, but I mean, I imagine like Copilot and other tools have really changed the way these classes are taught. Like, are they explicitly banned by classes, or how does that work?
Yeah, so language models and coding tools it's definitely a big hot topic in education right now, and different people handle it differently. In my courses, I say that they're not allowed to use Copilot for the assignments, but they're allowed to use it for the final project. And the final project is a big part of the grade. So even if they do find some way to not get the full experience out of the assignments, then they will be like kind of their understanding of the materials will be tested through the project component of the course. And then I know that like in the Intro AI course at Stanford, for example, I think they have a similar policy, and one other change that they made was they made the assignments worth less and the exams worth more because there's actually for the AI course, it's been offered many times, and the assignments are like a lot of students take the class, and so inevitably Copilot was trained on data that are like solutions to these homework problems.
Totally.
Unfortunately, and so because it was trained on that data, it's quite good at filling out the answers. Although maybe not always correctly, I think probably mostly correctly. So yeah, it's tricky, and I think it's best if assignments are robust to the use of Copilot, and project-based assignments are definitely like that. But at the same time, it introduces a lot of challenges, and part of the challenge is that if it was kind of trained on the assignments, it's very good. In other scenarios, like if you wrote kind of a new assignment and a new problem, then it might not work as well. And actually there are scenarios where it doesn't work as well. But then it's not practical to rewrite all of your homeworks every year. Usually your assignments get better and better as they get tested by students over quarters. And so that would lead to a worse experience for the students. But yeah, in general, in computer science, I think that we need to rethink the way that we're teaching it. I actually haven't talked to the intro computer science classes and seen how they're dealing with it, because it might change fundamentally the way that software developers are writing software.
Totally. As an aside, I've taken all these classes, so it's funny. I mean, but like 20 years ago, so it's funny to imagine like how they've evolved. Yeah. I think it was in C when I took it, incredibly. But I guess other than the work that we've talked about, what's like the research you're working on that you're most excited about?
Yeah, that's a great question. I'm really excited about robotics right now. I'm also, I guess one thing we haven't talked about is we've been developing, like we have a fairly low cost bimanual manipulation system. That means it has 2 arms, and we can do really dexterous tasks with it. We started doing a cooking task with it. We trained it to cook shrimp as our first task. That paper isn't quite public yet, but we're putting it out next week. So maybe by the time of the podcast, it will be out.
Wait, why do you need 2 arms to cook shrimp?
You might be able to do it just with 1 arm. The one part that we're doing that requires 2 arms is to flip the shrimp over. So we have a spatula, and we're also holding the pan with the left arm and then kind of flipping it that way. It's helpful, I think, to tilt the pan with the left arm when you're doing that. And this particular robot is actually on a mobile base, and so it actually, on top of that, also like picks up the pan, drives over to a bowl on the island of the kitchen, and then serves the piece of shrimp into the bowl.
Wild. Wow. How many shrimps have been cooked in this manner?
So it was actually trained only on 20 demonstrations. And so only 20 shrimps were used during, although I think that we might have collected some data before that during the iteration on the task. So it might be closer to 50. And yeah, although the performance is also, if we wanted higher performance, we would need to cook more shrimp. We've been feeding the shrimp to the graduate student who's been working on this, Zipeng. He's been feeding the shrimp to his cat.
I see.
So the shrimp is not going to waste.
How many times do you actually then cook the shrimp to test it? This is such a different world than what I'm used to.
Yeah, so usually if we have enough patients, usually we'll try to evaluate the policy through 20 trials, and we'll try to do that for every method or more. The more trials you do, the better statistical estimate of the performance you get. 20 is usually a pretty good number. And I think that for the shrimp evaluations we did lower because it involves cooking shrimp and so forth. But and so I think we might have only done 5 trials for the shrimp. I can't remember the exact number. But yeah, and if you are evaluating multiple methods, then yeah, per method evaluation in robotics actually gets quite expensive. And especially if you want to evaluate on multiple robot platforms, on multiple tasks, multiple methods, it really adds up, and you can't just like run a script that will evaluate everything for you. You need to be there with the robot.
And it seems like in this task, you eventually light your kitchen on fire or something, right?
Yeah, the pan that's actually being used in the experiments is my pan from home, and it's half black currently. And I hope that we'll be able to, clean the pan.
Amazing. And was it it's like a vision, like it's using vision too, along with manipulating?
It's using vision. We have 4 RGB cameras mounted on the robot, 2 actually mounted on each wrist of the robot, and 2 externally. Wrist-mounted cameras are actually really useful in robotics because you get a nice up-and-close view of what you're interacting with, and you also get these nice invariances where, like, if you're going to pick up an object, the object from the point of view of the wrist looks the same regardless of if you're like picking it up from like an angle versus if you're picking it up from a table. And that means that the data, the learning will be more data efficient because it'll learning to grasp from one orientation will teach you about how to grasp at other orientations as well.
Cool. Wow. What an amazing area of research.
It's a lot of fun.
It must feel so cool. All right. Well, I think we're out of time, so I'll let you go. But thanks, Chelsea. I appreciate your time. And
that was fun.
Cut it up. That was fun. Have a good one. Thanks so much for listening to this episode of Gradient Dissent. Please stay tuned for future episodes.